The universe is not playing by the rules. We look up at a night sky governed by elegant physics, only to find cosmic glitches that rewrite the textbooks. This journey explores 25 of the most baffling anomalies in space, phenomena that defy our current understanding of reality itself. By the end, you will see the cosmos not as a settled map, but as a frontier of profound and thrilling mystery. What unseen force is dragging entire galaxies off course? Why did a single radio signal from the void scream for just 72 seconds and then vanish forever? The answers, if they exist, are stranger than fiction. What do you think it means when the universe itself seems confused? Our own galaxy is not drifting aimlessly through the void. It is caught in a current, a relentless flow towards something we cannot see. This is the first great cosmic defiance, known as the Great Attractor. Picture the local group, our galactic neighborhood containing the Milky Way and Andromeda, all moving together. For decades, astronomers mapped this motion and found it was not random. Everything is being pulled toward a specific point in the constellation Centaurus, toward a gravitational focal point of unimaginable power. The sheer force required to tug hundreds of billions of stars suggests a mass perhaps 100,000 times greater than our entire Milky Way. Yet, when we point our telescopes toward that region of space, we see almost nothing. The Great Attractor lies directly behind the plane of our own galaxy, an area astronomers call the zone of avoidance. Here, the dense clouds of gas, dust, and stars of the Milky Way's core create an impenetrable cosmic curtain, blocking our view of the universe beyond. It is the ultimate cosmic irony, a mystery hidden in plain sight, or rather, hidden by our own celestial backyard. The leading theory suggests it is not a single, monstrous object, but an immense concentration of dark matter, the invisible scaffolding of the cosmos, woven together with thousands of galaxies in a supercluster we simply cannot see. Other ideas propose it could be the gravitational echo of an even larger structure beyond it, a pull from something greater still. Whatever it is, the Great Attractor forces a humbling admission. Our map of the universe has a colossal blank spot, and we are all falling toward it. But while the Great Attractor pulls at our galaxy with the silent force of gravity, another anomaly arrived as a sudden, deafening shout. On a quiet August night in 1977, a radio telescope at Ohio State University known as the Big Ear was performing its routine scan of the cosmos. The data printed out line by line on simple computer paper, a string of letters and numbers representing the strength of signals from deep space. Most readings were the usual background noise, coded as numbers and the occasional letter. Then at 10:16 p.m., the machine recorded something extraordinary. For exactly 72 seconds, a powerful, focused beam of radio waves slammed into the telescope. It was a narrowband signal, meaning it was tuned to one specific frequency, like a perfectly clear note played on a cosmic piano. That frequency was 1420 megahertz, a number that sent chills down the spines of the scientists who saw it. 1420 megahertz is the resonant frequency of neutral hydrogen, the most common element in the universe. It is considered a universal landmark, a logical channel any advanced civilization might use to announce its presence. The signal was so intense that the astronomer on duty, Jerry Amon, circled the alphanumeric sequence on the printout and wrote a single, famous word in the margin, "Wow," with an exclamation point. The WOW signal, as it became known, was a perfect candidate for an artificial extraterrestrial beacon. It came from a seemingly empty patch of sky in the constellation Sagittarius. It was incredibly strong, and it matched the precise profile scientists had predicted for an intentional signal. Yet, as quickly as it arrived, it vanished. Follow-up observations by the Big Ear and every other telescope that has ever listened since have heard nothing but silence from that exact spot. The signal never repeated. This single, lonely shout has fueled decades of speculation and debate. Could it have been a natural event, Some have proposed it was the hydrogen cloud of a passing comet, but detailed analysis showed no known comets were in that region at that time. Others suggest it might have been a reflected signal from a human satellite or piece of space debris, but the signal's characteristics and the technology of the era make that unlikely. The most enduring explanation, and the one that gives the WOW signal its legendary status, is that it was a one-time transmission from an intelligence far beyond our own. A cosmic lighthouse beam that swept past Earth for just over a minute, a message we heard but could not answer, or perhaps a signal never meant for us at all, just a fragment of communication that briefly crossed our path. It stands as a haunting reminder that in the vast quiet of space, a single moment of contact can redefine everything, and its enduring mystery lies not in what we heard, but in the profound silence that followed. If the WOW signal was a fleeting whisper, then dark flow is a relentless, silent river. It is a current not of water, but of entire galaxy clusters, hundreds of them, all moving together in the same direction at staggering speeds of over 2 million miles per hour. This is not the gentle drift of the Great Attractor. This is a coordinated exodus on a scale that defies everything we know about cosmic structure. Imagine throwing a handful of confetti into the air on a perfectly calm day, only to watch every single piece stream in unison toward the same distant horizon. That is the level of baffling coherence astronomers detected. They found this motion by studying the afterglow of the Big Bang itself, the cosmic microwave background. This faint radiation is the oldest light in the universe, a snapshot of the infant cosmos. As galaxy clusters plow through this sea of ancient photons, they leave a subtle imprint, a slight shift in the light's temperature known as the kinetic Sunyaev-Zeldovich effect. By mapping these tiny distortions, scientists could trace the cluster's motion. What they found was not the expected random jostling of a uniformly expanding universe. Instead, they saw a vast, coherent flow, a directional pull that seems to originate from a point far beyond the edge of everything we can see. This is where the standard model of cosmology breaks down. According to our best theories, the universe's expansion should be smooth and even on the largest scales, with matter distributed evenly enough that no single direction should have a gravitational monopoly. Dark flow suggests something immense is out there, exerting a pull so powerful it tugs at galaxies from a distance that light itself has not had time to cross since the beginning of time. The source of this pull must lie beyond our cosmological horizon, in a region of space-time that is causally disconnected from our own. We cannot see it, we cannot interact with it, yet its gravity reaches across the void to move the heavens. The implications are staggering. Could this be the gravitational fingerprint of another universe, a neighboring bubble in a vast multiverse brushing against our own? Or perhaps it is the remnant of some colossal structure that existed before our Big Bang, a scar on reality whose influence still echoes. Dark flow is more than an anomaly. It is a signpost pointing to a reality vastly larger and stranger than the observable universe we call home. The silence of dark flow is matched by a roar from our own galactic center, a roar we only learned to hear in the last 15 years. In 2010, scientists analyzing data from the Fermi Gamma Ray Space Telescope made a staggering discovery. Emanating from the very heart of the Milky Way, two colossal bubbles of ultra-high energy radiation balloon outward, one above and one below the galactic plane. These are the Fermi bubbles, and they are monstrous. Each bubble stretches for 25,000 light-years from its base to its edge. To grasp that scale, if you could stand on Earth and see one of these structures in the night sky, it would span half the heavens from horizon to zenith. They form a near-perfect hourglass shape, a symmetrical pair of cosmic balloons filled not with hot air, but with a seething fog of gamma rays and X-rays. This is the aftermath of a cataclysm, a fossil imprint of violence on a scale that dwarfs supernova. The leading suspect for this cosmic demolition is our galaxy's own supermassive black hole, Sagittarius A star. Normally quiet, astronomers theorize that millions of years ago it may have awakened in a spectacular feeding frenzy. As vast clouds of gas and dust spiraled into its event horizon, the black hole could have belched out twin jets of energy and matter at nearly the speed of light, inflating these gigantic cavities in the thin gas that permeates intergalactic space. An alternative theory points not to the black hole but to a frenzy of star birth. In this scenario, the galactic center experienced a starburst episode where thousands of massive stars were born in quick succession. These stars lived fast, died young, and exploded as supernova, their combined shockwaves blowing a gigantic bubble in the galactic halo. Yet both explanations face serious challenges. The bubbles are incredibly sharp-edged and symmetrical, which is difficult to achieve with messy, chaotic supernova explosions. And while the black hole jet theory is compelling, we see no such jets active today, and the energy required is almost incomprehensible. What event could have made our relatively quiet black hole scream with such force? The Fermi bubbles are a ghostly echo of that event, a reminder that our placid spiral galaxy has a temper. They hang there in the data, a pair of silent titans, challenging us to read their history in the faint glow of gamma rays, a message from a time when the core of our Milky Way was a place of unimaginable fury. While the Fermi bubbles are a monument to past violence, some stars behave in ways that suggest a strange and intricate present. Take the star known as KIC 8462852, but which the world now calls Tabby's star. Located over 1,000 light-years away in the constellation Cygnus, this otherwise ordinary star became infamous for one reason: it flickered. Data from the Kepler Space Telescope revealed its light was not just dipping periodically like a planet passing by, but plunging in bizarre, irregular, and dramatic ways. At times, the star's brightness would drop by a staggering 22%, a depth far beyond what any known planet could cause, and then it would recover in patterns that seemed almost chaotic. This was not a clean, repeating eclipse. It was as if something vast and complex was drifting in front of the star in a clumsy, unpredictable dance. The strangeness sparked a firestorm of speculation. Could it be a swarm of millions of comets breaking apart in a chaotic cloud? Perhaps it was the debris from a shattered planet, creating a colossal ring of dust and rock. And then came the most tantalizing idea of all. What if we were seeing the shadows of an alien megastructure? The concept of a Dyson sphere, a hypothetical swarm of energy-collecting satellites built by an advanced civilization, fit the data's requirement for something enormous and non-spherical blocking the light. For a time, Tabby's star became the best candidate in the galaxy for evidence of intelligence beyond Earth. Subsequent observations, however, have slowly dimmed that extraordinary possibility. Detailed studies of the star's light revealed that the dimming affected blue light more than red light. This is a classic signature of dust, not solid objects. Tiny dust grains scatter blue light, letting more red light pass through. The current scientific consensus now leans toward an uneven cloud of fine dust, possibly from a disrupted moon or a vast collection of icy bodies orbiting the star in a complex, clumpy disk. Yet, this mundane answer only deepens the mystery. What natural process creates such an immense, irregular, and dynamic dust cloud? Tabby's star remains a profound puzzle, a reminder that even when we rule out aliens, the universe can still cook up phenomena bizarre enough to make us consider them. If Tabby's star is a mystery of shadow, then the Red Rectangle Nebula is a mystery of light and form. Around a dying binary star system about 2,300 light-years away, this nebula presents a sight that seems to defy natural law. Through a telescope, it does not look like the classic wispy clouds of the Orion Nebula. Instead, it appears as a stark, almost man-made structure, a glowing red X shape with what looks like a series of evenly spaced rungs like a cosmic ladder. This geometric perfection is utterly alien in a cosmos governed by turbulence and chaos. The red glow comes from a specific type of carbon-rich dust being illuminated by the central stars, but the shape, that is the real enigma. How does a sphere of gas ejected from a dying star get sculpted into such precise, angular forms? The leading theory involves the central binary stars themselves. As they orbit one another, they may act like a spinning lawn sprinkler, channeling the outflow of gas and dust into two opposing cones. Our view from Earth looks directly down the barrel of one cone and sees the walls of the other, creating the illusion of an X. But that explains only the basic shape. The ladder rungs, those concentric, evenly spaced bars of dust that give the nebula its rectangular nickname, are far harder to account for. They suggest periodic pulses like a stellar heartbeat where the dying star puffs out material in regular intervals. As newer ejecta rams into older, slower-moving material, it creates shock waves that compress dust into these distinct shells. Yet the clockwork precision of these pulses is something our models of stellar death struggles to replicate. The red rectangle stands as a breathtaking cosmic sculpture, a natural phenomenon that looks impossibly artificial. It challenges our assumptions about how order emerges from chaos, proving that even in the final acts of a star's life, the universe can produce geometry so perfect it looks designed. The stark geometry of the red rectangle is a visible defiance, but the next anomaly is a hidden one, woven into the very fabric of the cosmos. It is called the axis of evil, and it is a pattern imprinted on the oldest light we can see. This light is the cosmic microwave background, the faint afterglow of the Big Bang that fills every corner of the universe like a fossilized whisper of creation. For decades, scientists have studied this microwave sky map, expecting it to be a random tapestry of hot and cold spots, a universe with no preferred direction, looking the same in all directions, a principle known as isotropy. But when they looked closer, they found something deeply unsettling. The distribution of these hot and cold spots is not perfectly random. They appear to align very subtly with the plane of our own solar system. It is as if the universe's birth certificate has a faint watermark that just happens to line up with our little corner of it. Statistically, the odds of this happening by pure chance are incredibly low, less than 1 in 1,000. This alignment suggests a preferred axis, a cosmic north, which directly contradicts the foundational assumption that the universe is isotropic and homogeneous on the largest scales. The implications of this are profound. If the axis of evil is real and not an illusion, it means the universe has a built-in directionality, a lopsidedness written into its origins. This would force us to rewrite the opening chapters of cosmic history. The leading explanations, however, try to preserve our standard models. One possibility is that it is a local contaminant, a foreground effect from our own Milky Way galaxy. Perhaps dust or magnetic fields within our galactic neighborhood are subtly distorting the signal, creating a false pattern. Another is that it is a statistical fluke, a strange alignment that, against all odds, just happens to exist from our particular vantage point. But if all these checks are done and the alignment remains, then we are left with a terrifyingly beautiful possibility that the universe is not the same everywhere. It would mean our place in the cosmos is not entirely accidental, that the echo of creation carries a faint memory of structure, a whisper of order that challenges our deepest assumptions about reality itself. While the axis of evil hints at a flaw in the universe's blueprint, a much smaller mystery played out for decades right here in our own solar backyard. Two robotic pioneers named Pioneer 10 and Pioneer 11 embarked on journeys to the outer planets and beyond, becoming humanity's first emissaries to the interstellar void. As they coasted away from the sun, their positions were tracked with exquisite precision by NASA's deep space network. Yet by the 1980s, a tiny, nagging discrepancy emerged in the data. Both spacecraft were slowing down just a little bit more than they should have been. This was the Pioneer anomaly, a minuscule, persistent deceleration toward the Sun. The force acting on them was incredibly weak, about 10 billion times weaker than Earth's gravity at our surface. To put that in perspective, it was like an extra weight of just over a pound pressing on a 1-ton car. But in the pristine, frictionless environment of deep space, where the equations of motion are supposed to be perfect, even this whisper of a deviation was a screaming contradiction. For years, it haunted physicists. Could this be the first tangible evidence of new physics? Some speculated it was a sign that our understanding of gravity itself was incomplete at very large scales, or perhaps an effect of dark matter subtly dragging on the probes. The anomaly became a classic puzzle, a demonstration of how the most precise measurements can reveal the most unexpected truths. The solution, when it finally came, was a masterpiece of scientific detective work and a lesson in humility. Decades after the anomaly was spotted, a team of researchers undertook a monumental effort to recover old engineering data, including the telemetry that tracked the temperature and power output of every system on the aging spacecraft. They built a complex thermal model of the Pioneers, which were powered by radioactive generators that produced both electricity and a lot of waste heat. The breakthrough came when they realized this heat did not radiate away from the spacecraft perfectly evenly. The heat from the power system was bouncing off the back of the spacecraft's large dish antenna, acting like a tiny, gentle photon rocket. Each infrared photon pushing off that surface imparted a minuscule amount of thrust, not away from the Sun, but subtly back toward it. When they summed up all these tiny, asymmetric pushes across the entire spacecraft, the calculated force matched the anomalous deceleration almost exactly. The mystery was solved not by rewriting the laws of physics, but by accounting for the engineering reality of the spacecraft themselves. The Pioneer anomaly's resolution is often called mundane, but its legacy is profound. It stands as a testament to the power of a persistent discrepancy. That tiny, unexplained drift forced scientists to examine their assumptions, to dig through decades of data, and to model their own technology with a precision never before attempted. It proved that the hunt for grand new physics often begins by meticulously ruling out every last mundane possibility, and that sometimes the universe's deepest secrets are hidden not in the distant cosmos, but in the gentle glow of a spacecraft's own waste heat. Deep within the heart of our galaxy, where the supermassive black hole resides, another enigma glows with an eerie, persistent light. The Fermi Gamma Ray Space Telescope has mapped this region in exquisite detail, revealing a bizarre and unexpected surplus of energy. Scientists call it the galactic center excess, a diffuse fog of gamma rays that blankets the core of the Milky Way. This isn't the structured fury of the Fermi bubbles, but a mysterious, uniform glow that shouldn't be there. Our models of the galactic center are crowded with known characters, pulsars spinning like lighthouses, clouds of gas being pummeled by cosmic rays, and the violent processes around the black hole itself. Yet when we add up all the light these sources should produce, there's a glaring gap. A massive excess of gamma rays remains, shining with no clear origin. This unexplained glow is concentrated exactly where our theories predict something else entirely should be, the densest concentration of dark matter in the galaxy. Dark matter, that invisible substance that makes up most of the universe's mass, is thought to form a vast spherical halo around the Milky Way, with its core at the galactic center. According to some leading theories, dark matter could be made of hypothetical particles called weakly interacting massive particles. If these particles are their own antimatter opposites, they might annihilate each other upon collision, converting their mass directly into energy and producing, among other things, a spray of gamma rays. The profile of the galactic center excess, its location, its energy signature, and its smooth distribution matches what many physicists predicted for such dark matter annihilation. It is, for some, the most compelling indirect evidence for dark matter we have ever seen, a potential whisper from the universe's most elusive substance. But science thrives on debate, and an alternative explanation has gained ground. Could this glow simply come from thousands of previously undetected millisecond pulsars? These are ancient, rapidly spinning neutron stars that act like cosmic flywheels, emitting powerful beams of gamma radiation. A vast, unseen population of these dim objects clustered in the galactic center could, in principle, produce a smooth, diffuse glow that mimics a dark matter signal. The problem is, our radio telescopes have not yet found nearly enough of them to account for the sheer intensity of the excess, so the mystery deepens. Is the glow a triumphant discovery, the first indirect glimpse of dark matter finally revealing itself through self-destruction? Or is it a cosmic camouflage, a veil cast by a teeming city of dead stars we have yet to fully census? The debate is fierce because the stakes could not be higher. One answer points to a fundamental new particle, the key to 85% of the universe's matter. The other points to a new understanding of stellar archaeology in our galaxy's crowded downtown. For now, the galactic center continues to radiate its cryptic signal, a puzzle written in the universe's most energetic language, waiting for our next generation of telescopes to translate. While the galactic center glows with hidden conflict, some galaxies wear their strangeness like a badge of honor in plain sight. Hoag's object is one of the most perfectly beautiful and perplexing sights in the cosmos. From our vantage point, it looks like a cosmic bullseye, a flawless ring of brilliant blue newborn stars encircling a dense golden core of ancient suns. Between these two distinct stellar populations lies a vast dark gap that appears almost completely empty. This is not how spiral galaxies like our Milky Way work, with arms winding continuously from the center. Hoag's object is a rare ring galaxy, and its pristine, symmetrical structure defies easy explanation. The leading theory suggests a galactic collision billions of years ago. Imagine a smaller galaxy plunging straight through the heart of a larger disk galaxy. The gravitational shockwave from that catastrophic encounter could have rippled outward, compressing gas and triggering a wave of star formation in a perfect circle, while leaving the central core relatively undisturbed. Yet there is a problem with this elegant story. In deep images, astronomers see no sign of a surviving perpetrator galaxy, no stellar debris that would be the obvious leftover of such a violent event. The emptiness around Hoag's object is profound, making the collision theory feel incomplete. Could it have formed from an unstable distribution of matter in the early universe, a rare and stable configuration that simply should not exist? Its serene perfection is a direct challenge, a galaxy that looks more like a piece of celestial art than a product of chaos and gravity. If Hoag's object is a puzzle of serene structure, then the Black Eye Galaxy is a portrait of cosmic violence frozen in time. Officially known as Messier 64, this spiral galaxy has a stunning and ominous feature, a sweeping, dark lane of thick cosmic dust that obscures part of its brilliant core, giving it the appearance of a bruised or blackened eye. This dust band is dramatic enough, but the galaxy holds a far stranger secret. In the late 1990s, astronomers studying the motion of gas within Messier 64 made a shocking discovery. The interstellar gas in the outer regions of the galaxy, thousands of light years from the core, is rotating in the opposite direction to the stars and dust in the inner disk. It is as if the galaxy has two counter-rotating components locked in a slow, silent tug of war. This is the unmistakable fingerprint of a past merger. Billions of years ago, a smaller, gas-rich galaxy likely collided with what is now the inner region of the Black Eye Galaxy. As the two systems merged, the incoming gas, carrying its original angular momentum, was forced into a retrograde orbit, spinning backward against the flow of the established stellar disk. The dark, obscuring dust lane we see is likely the turbulent frontier where these two opposing flows now collide and interact, a zone of intense compression where new stars are being born amidst the chaos. The mystery that remains is not the fact of the merger, but the specifics. What was the size and nature of the devoured galaxy? Why did its gas retain such a coherent, opposite motion instead of being fully assimilated? The Black Eye Galaxy is a cosmic crime scene, and the contradictory motions of its components are the lasting evidence telling a story of a catastrophic encounter that we can only piece together from its beautiful, bruised aftermath. From galactic collisions and counter-rotating disks, we now journey into a realm of profound absence. The Boot's void is not an object, but the staggering lack of them. Imagine a sphere of space so vast it could contain thousands of galaxies like our Milky Way, yet when you look inside, you find almost nothing. This cosmic desert, over 330 million light-years across, is one of the largest known structures in the entire universe, defined entirely by what is not there. In a cosmos where matter clumps into filaments and walls like a colossal sponge, the Boot's void is a gaping hole. If our Milky Way sat at its center, we would have had no notion of other galaxies until the 1960s. The sheer scale of this emptiness directly challenges our models of how the universe arranged itself after the Big Bang. Gravity should have pulled matter into a more even distribution, not left a vacancy the size of a supercluster. So what could have carved out such a nothing? One leading theory suggests it is not a single void, but the merger of several smaller voids that grew together over billions of years, like soap bubbles coalescing into one gigantic cavity. Yet, even this feels insufficient for the staggering scale. More exotic ideas reach back to the universe's first moments, proposing that the void is a fossil of an enormous quantum fluctuation, a region where the density of matter was inexplicably low from the very beginning, and that initial deficit simply inflated with the expansion of the universe itself. The void is not completely empty. Astronomers have identified a handful of lonely galaxies drifting in this immense darkness, like single ships on an ocean that spans millions of light-years. Their very existence is its own mystery. How did these isolated islands of stars form and survive in such a barren expanse? The Boot's void forces us to confront a humbling truth. Our maps of the cosmos are not just charts of light and matter, but also of shadow and void. It stands as a monument to absence, a reminder that understanding the universe requires us to explain not just the crowded places, but the terrifyingly empty ones as well. The profound emptiness of the Boot's void is a monument to cosmic scale, but our own solar system holds a geometric wonder that is just as defiant. At Saturn's North Pole, a storm rages with a precision that seems mathematically impossible. This is the Saturn hexagon, a colossal, six-sided jet stream etched into the atmosphere of the gas giant. It is a perfect polygon, a shape you'd expect in a geometry textbook, not churning in the clouds of a distant world. This hexagon is staggeringly large, with each side measuring about 8,500 miles long. The entire structure is so vast that two planet Earths could fit side by side within its boundaries. But its size is rivaled only by its endurance. First spotted by the Voyager probes in the 1980s, it has persisted for at least 4 decades, and likely for centuries more, a permanent feature in a dynamic, turbulent atmosphere. How can a storm, a chaotic system by nature, maintain such a rigid, angular shape for so long? The answer appears to lie in the physics of spinning fluids. Here on Earth, scientists have recreated similar polygonal shapes in the lab. By placing a fluid in a circular container and spinning it at just the right speed, they can generate stable standing waves that form shapes with 3, 4, 5, or 6 sides. It is a demonstration of how simple rotational forces can impose order on chaos. The Saturn hexagon is likely a giant version of this lab experiment, a standing wave pattern in the planet's fast-moving polar jet stream, sculpted by the complex interplay between wind speeds, atmospheric density, and Saturn's own rapid rotation. Yet the laboratory models only take us so far. They explain the how of the shape's formation, but not the why of its incredible longevity and perfection. Saturn's atmosphere is a seething cauldron of storms and shear, a system that should erode or distort such a precise pattern over time. What unique and stable conditions at that exact latitude have locked this atmospheric tattoo in place, season after season, for generations? The hexagon is more than a curiosity. It is a natural laboratory at a planetary scale, challenging our understanding of fluid dynamics in an environment we can never truly replicate. It stands as a stark reminder that even within our own celestial neighborhood, nature can produce artistry of breathtaking and enduring precision. Saturn's perfect hexagon is a storm shaped by predictable physics, but the solar system's next visitor seemed to follow no rules at all. In October 2017, astronomers at the Pan-STARRS telescope in Hawaii spotted a faint point of light moving at breathtaking speed. Its trajectory was unlike anything seen before, a hyperbolic path so extreme it could only mean one thing: this object was not from here. It was the first confirmed interstellar visitor ever detected passing through our solar system, and they named it Oumuamua, a Hawaiian word meaning scout or messenger from the distant past. From the moment of its discovery, Oumuamua was an outlier. Its brightness varied dramatically as it tumbled through space, suggesting an extreme, elongated shape. Calculations showed it was likely 10 times longer than it was wide. A cigar or pancake-shaped object hundreds of meters in length, tumbling chaotically end over end. This was already strange, as most natural bodies in our solar system are more rounded, but the real mystery came as it sped away from the sun. After its slingshot around our star, astronomers tracked its path with extreme precision. They found it was not just coasting under the sun's gravity alone. Oumuamua was accelerating ever so slightly on its way out of the solar system. This is a behavior comets often exhibit as sunlight heats their icy surfaces, causing jets of gas and dust to erupt and act like a gentle rocket engine. This process, called outgassing, leaves a clear signature, a visible cloud of gas and dust called a coma, and often a tail. Yet every telescope pointed at Oumuamua saw nothing. No coma, no tail, no dusty envelope of any kind. It was accelerating in total silence with no visible mechanism to push it. This non-gravitational acceleration sent scientists scrambling. If it wasn't outgassing, what was it? One hypothesis proposed it was a hydrogen iceberg. In the cold depths of interstellar space, a chunk of solid hydrogen could have formed. As it neared the sun, the heat would cause the hydrogen to sublimate, providing thrust without leaving a dusty trail, since hydrogen is invisible in the wavelengths we typically observe. The problem is, a hydrogen iceberg is incredibly fragile, likely unable to survive the journey through interstellar space or the heat of a close solar pass. Another, more recent idea suggests it could be a fragment of a nitrogen iceberg, perhaps chipped off a Pluto-like world in a distant star system. Nitrogen outgassing could, in theory, provide the thrust without a prominent coma. But this, too, requires a very specific and unlikely series of events to explain the object's origin and survival. The most famous and most controversial explanation came from Harvard astronomer Avi Loeb, who suggested the acceleration could be explained by solar radiation pressure. If Oumuamua was extremely thin and lightweight like a solar sail, the physical push of sunlight itself could have provided the extra kick. This would require an object unlike any asteroid or comet we know, one with the geometry and density of a manufactured object. While most scientists favor a natural origin, the key point is that no single natural explanation has yet gained universal acceptance. Oumuamua's silent acceleration remains an open case, a one-of-a-kind data point from the vast interstellar ocean. It was a messenger that delivered its note and sped away before we could fully decipher the writing, leaving behind a fundamental question. Are we looking at a strange new type of natural debris or something else entirely? But the story of Tabby's star did not end with its strange flickers. As astronomers delved deeper, they uncovered a second, even more baffling layer to its mystery. By examining over a century's worth of archival photographic plates from various observatories, a startling trend emerged. Beyond those erratic, day-long dips, the star's overall brightness has been steadily and significantly fading for more than 100 years. This is not a quick wink, but a long, slow dimming that has seen the star lose a substantial portion of its light over decades. Think of it like a lamp with a faulty switch that occasionally flickers, but over your entire lifetime, you also notice its bulb is gradually, inexorably growing dimmer. This secular dimming, as it's called, throws a wrench into the simpler explanations. A cloud of dust from a shattered comet or a colliding family of asteroids might explain the short-term dips, but such a cloud should not linger for a century. Over time, the dust should either dissipate into space, fall into the star, or clump together into planets. It should not maintain a perfect, opaque veil that consistently blocks more and more light year after year. This relentless fade complicates the dust theory immensely, forcing scientists to ask, what natural process could possibly produce a long-term, structured dimming of this magnitude? It revives the door to more exotic possibilities. Could we be witnessing the slow, deliberate construction of a vast megastructure, one that is progressively encircling the star and capturing its energy? While still considered a far less likely explanation, the long-term dimming is precisely the kind of signature such an ambitious project might create. More plausible natural theories have scrambled to adapt. Perhaps the star is surrounded by a vast, misshapen disk of dust and debris, warped by the gravity of an unseen planet, and our solar system's line of sight is slowly passing through its thickest, darkest region. Or maybe Tabby's star itself is undergoing a rare and unstable phase, dimming from within due to some internal process we do not yet understand. The key point is this: Tabby's star is not just a star with odd transits. It is a star that is fundamentally changing in brightness on a human timescale, presenting two distinct puzzles: the chaotic short-term dips and this relentless long-term slide into shadow. This dual mystery makes it one of the most compelling and frustrating objects in the sky, a reminder that some cosmic riddles only deepen the longer we stare at them. The long, slow dimming of a single star is a puzzle on a human scale, but the next anomaly is woven into the very architecture of the cosmos, challenging the foundation of modern cosmology. This is the dark matter halo problem, and it is not about finding dark matter, but about understanding how it behaves. Our most sophisticated supercomputer simulations of the universe, based on the incredibly successful cold dark matter model, paint a very specific picture. They tell us that dark matter, the invisible gravitational glue holding galaxies together, should form halos with a distinct density profile. Imagine a steep, concentrated peak at the very center of a galaxy, a sharp cusp where dark matter is densely packed, with the density falling off rapidly as you move outward. This cuspy halo is a direct prediction of how this cold, slow-moving substance should collapse under gravity alone. Yet, when astronomers look at real dwarf galaxies, the smallest and most dark matter-dominated galaxies we can study, they see something completely different. The dark matter in these galaxies appears to be distributed in a smooth, gentle core, like a soft hill rather than a sharp mountain peak. This glaring mismatch between the simulated cusp and the observed core is one of the most persistent headaches in astrophysics, known as the core cusp problem. How could the universe's simulations be so spectacularly right on the largest scales, yet so seemingly wrong on the scale of individual small galaxies? One compelling line of thought points not to a failure of dark matter, but to the power of ordinary matter. Stars, gas, and the supernova explosions that end massive stellar lives are not just passive passengers in these dark matter halos. They are active shapers. The theory goes that in the early, violent lives of dwarf galaxies, cycles of intense star formation and catastrophic supernova could have acted like cosmic bombs. These explosions would have blown huge amounts of gas outward, and as that gas moved, its gravity would have tugged on the dark matter, effectively dragging it from the center and smoothing out the sharp cusp into a gentle core. It is a story where the tiny fraction of the universe we can see, the normal matter, fights back against the overwhelming dark majority, sculpting it through sheer astrophysical violence. But if this explanation holds, it means our models of how stars and gas interact in these tiny galaxies are far more complex and powerful than we ever imagined. The core cusp problem is not alone. It has a companion puzzle called the missing satellites problem. Those same universe simulations predict that hundreds of small, dark matter clumps should be swarming around a galaxy like our Milky Way, each massive enough to host its own tiny dwarf galaxy. But when we count the actual satellite galaxies orbiting our home, we find only a few dozen. Where are all the rest? Have they simply failed to light up with stars, remaining as pure dark matter ghosts invisible to our telescopes? Or did the process of galaxy formation in such small halos somehow get suppressed? Once again, the answer may lie with that ordinary matter. Perhaps the intense radiation from the first stars and galaxies, or the heating from those same supernova, blew away the gas needed to form stars in the smallest clumps, leaving them dark and nearly undetectable. Together, these two problems, the core cusp and the missing satellites, represent a profound tension. They suggest that the simple, elegant story of dark matter's gravitational dominance is incomplete. The luminous tail of the cosmic dog, the normal matter that makes up you, me, and every star we see, might be wagging the dark, invisible beast far more than our theories predicted. Solving this requires not just a better particle for dark matter, but a revolutionary understanding of how light and shadow, the seen and the unseen, dance together across billions of years to build the galaxies we observe today. These galactic scale puzzles find their echo in the immense structures that bind the cosmos together, beginning right here in our own stellar neighborhood. Wrapping around the Milky Way like a faint cosmic necklace is a mysterious stream of stars known as the Monoceros ring, or sometimes the unicorn. This vast, looping band of ancient stars is not part of our galaxy's classic spiral structure. Instead, it forms a distinct, ring-like path that orbits above and below the galactic plane, stretching across an enormous swath of sky. The prevailing theory is a story of galactic cannibalism. Billions of years ago, a small, unfortunate dwarf galaxy ventured too close to the immense gravitational pull of the Milky Way. Our galaxy's tidal forces, the difference in gravity between the near and far side of the intruder, stretched it apart like cosmic taffy. The stars of that dwarf galaxy were not swallowed whole, but were instead strung out into a long, looping river that continues to orbit us today, a stellar fossil of a long-finished meal. Yet, the exact identity of the victim and the timing of this event remain hotly debated. Some analyses suggest the ring is too vast and contains too many stars to have come from a single, small dwarf galaxy. Could it be the disrupted remains of several mergers, or is it a surprising ripple in the Milky Way's own disk, thrown out of shape by a close encounter with another galaxy? The unicorn reminds us that our home galaxy is not a static island, but a dynamic, ever-changing structure still bearing the scars of its violent growth. If the Monoceros ring is a relic of a local demolition, then the next structure is a monument of such staggering scale it seems to defy the universe's own rules. Far beyond our local galactic neighborhood, deep in the distant cosmos, lies the Hercules Corona Borealis Great Wall. This is not a physical wall, but a colossal filament, a gauzy thread of galaxy clusters and superclusters bound together by gravity. Its scale is almost incomprehensible. It stretches for over 10 billion light-years from end to end. To grasp that, a beam of light traveling at the universe's ultimate speed limit would need more than half the age of the entire universe just to traverse its length. This makes it a candidate for the single largest known structure in all of existence, and that is precisely where the profound puzzle lies. Its sheer size presents a direct challenge to a cornerstone of modern cosmology, the cosmological principle. This principle states that, when viewed on a sufficiently large scale, the universe should look roughly the same in every direction and from every location. Matter should be distributed homogeneously. There should be no preferred places and no structures so enormous they break the statistical mold of a smooth, uniform cosmos. The Hercules Corona Borealis Great Wall appears to do just that. A structure of this magnitude should not exist under our standard models. It is like finding a single mountain range that spans an entire continent on a globe that's supposed to be perfectly smooth. Its discovery forces astronomers to ask a fundamental question: is this wall a statistical fluke, a rare but possible clustering in an otherwise uniform universe? Or is it a sign that the cosmological principle itself has limits, that the universe's largest structures can grow to sizes we never thought possible, revealing a cosmos with a graininess and architecture far grander than we imagined? The grand structures of the cosmos are built from a handful of simple ingredients forged in the universe's fiery first moments. Yet one of those primordial ingredients has never quite added up. In the first 3 minutes after the Big Bang, the cosmos was a seething nuclear furnace, fusing protons and neutrons into the universe's first atomic nuclei. This process, called Big Bang nucleosynthesis, produced vast amounts of hydrogen and helium, with trace amounts of two heavier elements, deuterium, and one specific isotope, lithium-7. Our mathematical models of this explosive birth are exquisitely precise, allowing us to calculate exactly how much of each element should have been created. For deuterium and helium, the amounts we observe in the oldest regions of space match the predictions almost perfectly. It is a triumphant confirmation of our understanding of the universe's first moments. But for lithium-7, the numbers are catastrophically wrong. The oldest stars in the Milky Way, pristine fossils from the early universe that should preserve its original chemical makeup, show only about 1/3 the amount of lithium our models insist should be there. It is as if the universe's recipe book has a glaring typo, a missing ingredient in the story of creation itself. This is the cosmological lithium problem. For decades, physicists have wrestled with this elemental discrepancy. Could our understanding of nuclear physics in those extreme first minutes be incomplete? Perhaps unknown particles, like certain types of dark matter, existed in the early plasma and subtly altered the rates of key nuclear reactions, diverting the production line away from lithium. Another possibility points not to the birth of lithium, but to its potential destruction. Maybe these ancient stars are not perfect time capsules after all. Their interiors are churning cauldrons, and over billions of years, they might have dragged surface lithium down into their hotter cores, where it was fused into other elements and destroyed. The problem is, our best models of stellar interiors struggle to show this process happening efficiently enough to account for the threefold shortage. Some astronomers have proposed more exotic stellar activity, like unseen planets falling into the star and stirring its layers, to explain the destruction. Yet each proposed solution creates new complications, and none has achieved a consensus. The lithium problem endures as a quiet but profound crack in the foundation of cosmology. It tells us that our otherwise successful story of the universe's origin is missing a page, a paragraph that explains how the third, simplest element in existence somehow slipped through the cracks of time. If lithium is a missing piece of the cosmic recipe, then some galaxies are built from a recipe we can barely read at all. Drifting silently in the dense coma cluster, a collection of thousands of galaxies over 300 million light-years away, there is a ghost. Its name is Dragonfly 44, an ultra-diffuse galaxy that defies every expectation of what a galaxy should look like. From our telescopes, it appears as a faint, wispy smudge of light, a celestial cloud so dim it was only discovered in 2015. At first glance, it seemed unremarkable, a dwarf galaxy with perhaps 100 million stars, a tiny, failed collection in a crowded metropolitan cluster. But when astronomers measured the motions of its sparse stars, they received a profound shock. Those few stars were moving at blistering speeds, orbiting so fast that the galaxy's own gravity should not be able to hold them together. The only possible explanation was the presence of an immense, invisible anchor, a colossal halo of dark matter. The calculations revealed a truth that is almost impossible to comprehend. Dragonfly 44 has roughly the same total mass as our own Milky Way galaxy. Yet, while the Milky Way blazes with hundreds of billions of stars, Dragonfly 44 contains less than 1% of that number. This means that over 99.99% of its mass is not stars, not gas, not dust, but pure, invisible dark matter. It is a galaxy where the dark matter skeleton is fully formed, but the luminous flesh of stars barely clings to it at all. Think of it as finding a human skeleton the size of a blue whale, but with only a handful of skin cells scattered across its immense frame. How does such a phantom galaxy even exist, especially in a violent environment like the Coma Cluster? Galaxy clusters are cosmic demolition derbies where tidal forces and collisions rip apart fragile structures. A wispy cloud of stars with so little visible matter should have been shredded and absorbed by its massive neighbors eons ago. The fact that Dragonfly 44 survives tells us its dark matter halo is not just massive, but incredibly robust, a gravitational fortress that protects its meager stellar population. This presents a monumental puzzle for theories of galaxy formation. Did it form with a normal amount of gas that was somehow stripped away before it could condense into stars, leaving behind a dark matter scaffold and a few stragglers? Or was it always anemic, born in a region of the early universe that was mysteriously starved of the raw materials needed for star birth? Its existence suggests a hidden population of similar dark galaxies, cosmic phantoms that have been hiding in plain sight because they emit almost no light for us to see. Dragonfly 44 is more than a curiosity, it is a nearly pure laboratory. By studying how its few stars move within this vast dark matter cocoon, scientists can map the distribution and behavior of dark matter with minimal interference from the messy astrophysics of gas and star formation. It is a direct window into the universe's dominant but invisible component, a ghostly galaxy that, by being almost nothing, tells us everything about the hidden architecture of reality. Our galaxy's dark matter ghosts are a puzzle of profound emptiness, but on a dusty, rust-colored world next door, a tantalizing scent has been detected. The thin, cold atmosphere of Mars holds a secret, a whiff of a gas that should not be there, or at least should not behave as it does. This is the Mars methane mystery. Since 2004, various orbiters and most notably the Curiosity rover on the surface have reported intermittent detections of methane gas. These are not steady readings, but sudden, localized spikes where methane concentrations soar to around 10 times the background level, only to vanish again within weeks or even days. On Earth, methane is a powerful biosignature. The vast majority of it in our air is produced by living organisms, from microbes in wetlands to the digestive systems of cattle. Its presence on Mars immediately raises the electrifying question: could this be a sign of Martian life, perhaps subterranean microbes eking out an existence deep below the frozen soil? But science demands caution. Methane can also be produced abiotically without life through a geological process called serpentinization. This occurs when certain types of iron-rich rocks, like olivine, react with water in a chemical process that releases methane as a byproduct. Mars has plenty of the right rocks and strong evidence of past and possibly present subsurface water, so the detective work begins. Is the gas geological or biological? The mystery deepens because of the gas's bizarre behavior. Mars has an active atmosphere with ultraviolet light from the sun that breaks down methane molecules. Based on our understanding of this photochemistry, any methane released should linger in the atmosphere for several hundred years before dispersing. Yet the observed plumes appear and disappear on a timescale of mere weeks. This suggests something is actively destroying the methane much faster than expected. Or perhaps the methane is being released in such small, localized bursts that it quickly dilutes below detection limits. Could there be an unknown catalyst in the Martian soil, a mineral that rapidly eats the gas? Or are the plumes so pinpoint in origin that our current instruments simply cannot track their full life cycle? The debate is fierce and complicated by immense technical challenges. Distinguishing between Martian methane and potential contamination from the rovers themselves is a constant concern. Different instruments, like the European Space Agency's Trace Gas Orbiter, have sometimes failed to detect methane from orbit during times when Curiosity reported a spike, adding another layer of contradiction. This back and forth makes Mars methane one of the most compelling and frustrating puzzles in astrobiology. It is a ghostly signal, a whisper of possibility that flickers in and out of existence, refusing to be pinned down. Every new detection sends a jolt of excitement through the scientific community, and every subsequent failure to confirm it reinforces the maddening complexity of the hunt for life next door. The answer, when it finally comes, will not be a simple yes or no. It will be a story written in chemistry and geology, a tale of whether the red planet is merely geologically grumbling, or if, in some hidden aquifer or deep rock fracture, something is quietly, intermittently breathing. The faint scent of a distant world's atmosphere is a whisper compared to the cosmic scream that arrived from the void on an October night in 1991. High above the Utah desert, the Fly's Eye cosmic ray detector caught a single, subatomic visitor, a proton moving with energy so incomprehensible it was immediately dubbed the "Oh my God" particle. Its energy was a staggering 20 times greater than the most powerful particles produced in our largest human-built accelerators, like the Large Hadron Collider. To put this into a human scale, imagine the kinetic energy of a baseball pitched at 60 miles per hour, packed into a single, fundamental particle smaller than an atom. The forces required to accelerate a proton to such a velocity are almost unimaginable, the stuff of galactic cores and colliding galaxy clusters. Yet this particle's existence creates a profound paradox, a cosmic speed limit it seemingly broke. According to a well-established principle called the Greisen-Zatsepin-Kuzmin, or GZK limit, ultra-high energy cosmic rays should not be able to travel vast intergalactic distances. The universe is not empty, it is filled with the faint afterglow of the Big Bang, the cosmic microwave background. A proton traveling at such a ludicrous fraction of light speed would constantly collide with these ancient photons. Each collision would rob it of energy, like a marathon runner constantly battered by a hail of pebbles. Over millions of light years, this process should grind even the most energetic particles down below the GZK threshold. The "Oh my God" particle, therefore, presents a twofold mystery. First, what celestial monster could possibly act as a particle accelerator of such ferocious power? Candidates include the violent environments around supermassive black holes, the shock waves of merging galaxy clusters, or even the cataclysmic deaths of hypermassive stars. But none of our models easily produce a single particle with quite that much punch. Second, and perhaps more baffling, where did it come from? When astronomers traced its probable path back into the depths of space, its arrival direction pointed to a seemingly empty void, a region of space with no known galaxies, quasars, or other obvious cosmic power plants. It is as if a cannonball was fired at us from an abandoned field. This suggests either our maps of the universe's energetic objects are woefully incomplete, or there are processes of particle acceleration at work that we have not yet begun to dream of. The oh my God particle was a solitary messenger, a data point of one that defies our understanding of both the universe's most powerful engines and the highway it traveled to reach us. The violence of a star's death is supposed to be a singular, definitive event, but in the depths of a galaxy 600 million light-years away, a black hole staged an encore. Astronomers watched as a star drifted too close to a supermassive black hole, a gravitational monster with the mass of millions of suns. The star was stretched and shredded by immense tidal forces, a process known as a tidal disruption event. The initial cataclysm, named Assassin 14 Li, was a brilliant flare of X-rays and ultraviolet light as the star's debris spiraled into the black hole's accretion disk, heating to millions of degrees. It was a textbook feast, and scientists expected the glow to gradually fade over months or years as the last of the stellar material was consumed. Then, something impossible happened. Roughly 2 years after the initial eruption, the black hole flared brightly again. This was not a faint echo, but a significant new outburst of energy. It was as if a funeral pyre, having burned down to embers, suddenly roared back to life with a fresh log thrown onto it. The problem is, in a standard tidal disruption event, there should be no fresh log. The star is completely destroyed in one go, its debris forming a temporary accretion disk that steadily drains into the black hole. Once that fuel is gone, the show is over. The repeating outburst of Assassin 14 Li defies this simple narrative. So what reignited the black hole's appetite years after its meal? One leading theory is as elegant as it is brutal. Perhaps the star was not completely obliterated on its first pass. A sizable fragment, maybe its dense core, could have been flung onto a highly elongated orbit. For years, this stellar survivor journeyed through the darkness on a cosmic ellipse, only to swing back near the black hole and be stripped of another layer of gas, feeding a second course to the waiting monster. This scenario paints a picture of drawn-out torture, a star being slowly peeled apart over multiple orbits. Another possibility digs into the complex physics of the accretion disk itself. The swirling maelstrom of gas and dust might not be stable. It could develop clumps or experience sudden shifts in magnetic fields, causing pockets of material to plunge into the black hole all at once, years after the initial disruption. This would be like a logjam in a river suddenly breaking, releasing a surge of water long after the upstream rain has stopped. Both explanations reveal a fundamental truth: our models of these extreme events are still in their infancy. We imagine tidal disruption events as simple, one-act tragedies. Assassin 14 Li shows they can be complex serials with chapters separated by years of silence. It forces us to reconsider the final moments of a star, not as an instant of destruction, but as a potential sequence of calamities, and to see the black hole not just as a passive consumer, but as a diner that might save a piece for later. While the oh my God particle hints at unseen cosmic accelerators, and the repeating black hole feast reveals hidden chapters in stellar destruction, our final two anomalies force us to step back and question the canvas of reality itself. The first is a chill in the oldest light in the universe. Embedded in the detailed map of the cosmic microwave background, that fossilized glow from the Big Bang is a region of space that is just too cold. Known simply as the cold spot, it is an area of the sky about 5 times larger than a full moon, where the microwave radiation is significantly cooler than the surrounding average. This isn't a tiny statistical blip. Its size and intensity make it a genuine outlier in an otherwise remarkably uniform cosmic tapestry. For such a large, cold patch to exist by pure random chance is incredibly unlikely, with odds estimated at around 1 in 200. So what cast this cosmic shadow? One leading explanation is a supervoid, an enormous region of space largely empty of galaxies and galaxy clusters. According to a phenomenon called the integrated Sachs-Wolf effect, as light travels through the expanding universe, it can gain or lose energy when passing through vast gravitational hills and valleys. If the cold spot is caused by a supervoid, photons entering this underdense region would lose a tiny bit of energy climbing out of its weakened gravitational well, stretching their wavelength and making the light appear cooler. The problem is, when astronomers went looking for this proposed void, they found one, but it's not quite big enough. The observed underdensity of galaxies, while vast, doesn't seem to have sufficient depth or size to account for the profound coldness we see. It's like finding a dip in the road, but not one deep enough to explain the massive jolt your car just felt. This discrepancy has led to more exotic theories. Perhaps the cold spot is not a void at all, but a cosmic texture defect. In the frenetic first moments after the Big Bang, as the fundamental fields of the universe underwent phase transitions, topological defects could have formed, like cracks freezing into ice. A specific type of defect, a texture, could have created a localized gravitational well that left this permanent cold imprint on the CMB. Another, even more mind-bending possibility is that the cold spot is evidence of a collision with another universe in the multiverse, a bruise on our cosmos from a primordial impact. While this remains highly speculative, the cold spot's enduring mystery is clear. It is a feature that challenges our understanding of the universe's large-scale structure and its earliest moments. This question of cosmic smoothness leads directly to the final, and perhaps most personally relevant, large-scale anomaly. What if the cold spot is a distant curiosity, but we ourselves are living in a local anomaly? This is the provocative claim of the KBC void, named for the astronomers who proposed it. Their analysis suggests we are not in an average region of the cosmos, but reside in a staggeringly large local underdensity, a bubble of relative emptiness about 2 billion light-years across. In this model, the Milky Way sits within a vast, nested series of galactic voids, making our local universe significantly less dense than the cosmic average. If true, this has profound consequences for cosmology's most critical measurements. The expansion rate of the universe, known as the Hubble constant, is measured by observing distant supernova and other standard candles. If those objects are sitting outside our local void, in a denser region of space, the local curvature and gravitational environment could subtly alter our perception of their distance and redshift. This could potentially resolve one of the biggest tensions in modern cosmology, the Hubble tension, where different methods of measuring the universe's expansion rate disagree. Furthermore, the inferred strength of dark energy, the mysterious force accelerating cosmic expansion, is calculated based on the assumption that we live in a representative region. If we're in an underdense bubble, our measurements of dark energy's effects might be skewed, like trying to judge the ocean's current while floating in a calm lagoon. The controversy is fierce. Many cosmologists argue that the evidence for such a gigantic void is not strong enough, and that it would severely violate the cosmological principle, the foundational idea that the universe is homogeneous on large scales. They contend that galaxy surveys, while showing some local variations, do not support a void of the scale and emptiness required. Yet, the KBC void hypothesis persists as a bold challenge. It forces us to confront a humbling possibility that our entire view of the cosmos, from its expansion to its ultimate fate, might be filtered through a lens of local exceptionalism. We may not be at the center of the universe, but we could very well be sitting in one of its quietest, most empty neighborhoods, a fact that would forever change how we interpret the light from the distant, crowded streets beyond. These cosmic glitches are not random errors, but cracks in a single, unified picture of reality. When we step back from each individual mystery, a startling pattern emerges. Many of them point not just to what we don't know, but to where we might be looking for answers. Consider the profound directional pulls, the cosmic currents like dark flow that tug galaxies toward an unseen horizon, or the eerie alignment of the universe's oldest light with our solar system in the axis of evil. These are not just measurements gone wrong. They are potential signposts hinting that influences from beyond our observable horizon, from realms of space and time we can never directly see, are actively shaping the cosmos we inhabit. It suggests our universe may not be a closed, self-contained system, but one that feels the gravitational breath of something vastly larger, perhaps a multiverse of neighboring realities. Simultaneously, another set of anomalies drills down into the bedrock of physics itself. The stubborn shortage of primordial lithium, the ghostly behavior of dark matter in dwarf galaxies, the impossible endurance of Saturn's hexagon. These are not problems of distant influence but of incomplete law. They indicate gaps in our understanding of the fundamental forces and particles that govern everything from the first 3 minutes of creation to the weather on a gas giant. The universe seems to be operating by rules we have not yet fully written down. This duality is the true power of these 25 cosmic anomalies. They are not isolated curiosities to be solved one by one. They are interconnected stress points, the places where our most cherished cosmological models bend and groan under the weight of new evidence. Each one is a potential key, not just to its own solution, but to a revolutionary, deeper understanding of the universe's true, and likely far stranger, nature. This grand puzzle, spread across the entire sky and woven into the fabric of reality itself, demands a new generation of eyes. We have reached the limit of what our current telescopes can tell us, but a new era of cosmic exploration is just beginning. The answers to these 25 anomalies and the discovery of the next ones will come from a suite of revolutionary instruments now coming online or being built. First, consider the Vera C. Rubin Observatory in Chile. Its primary instrument, the Legacy Survey of Space and Time, will not study a single object but the entire visible sky every few nights for a decade. It will create the greatest cosmic movie ever made, a time-lapse of the universe. This relentless gaze will catch things in the act. It will find millions of new transient events, spotting the flickers of stars like Tabby's star with unprecedented regularity, and cataloging tidal disruption events to see if repeats like Assassin 14 Lie are common or freak occurrences. It will map the subtle distortions of billions of galaxies, creating the most detailed chart of dark matter ever conceived, directly testing the core cusp problem in thousands of dwarf galaxies and hunting for phantom structures like the Great Attractor. And it will sweep the solar system's frontiers, likely finding dozens of interstellar visitors like Oumuamua, finally giving us a population to study instead of a single, baffling data point. While Rubin scans the sky in breadth, the James Webb Space Telescope peers into impossible depth. Its infrared eyes are designed to look back in time, to the very first galaxies that flickered on after the Big Bang. By studying the pristine light of these ancient systems, Webb can probe the conditions of the early universe, searching for clues to the lithium problem and observing how dark matter halos first gathered their stars. It will dissect the atmospheres of exoplanets, searching for biosignatures, and study the dusty disks around young stars to understand the formation of bizarre geometries like the red rectangle. Webb's successor, the Nancy Grace Roman Space Telescope, will combine these strengths. With a field of view 100 times larger than Hubble's, Roman will conduct wide-field surveys in infrared with Webb's sharpness. It will perform a galactic census of unprecedented scale, mapping the distribution of galaxies and dark matter to definitively test the cosmological principle and measure the true scale of structures like the Hercules Corona Borealis Great Wall. It will hunt for rogue planets drifting between stars and survey the galactic bulge to find the population of faint pulsars that might explain the galactic center excess or rule them out entirely. On the ground, a different kind of eye is taking shape. The Square Kilometer Array, a radio telescope network spanning 2 continents, will listen to the universe's quietest whispers. By mapping the distribution of neutral hydrogen, the most abundant element across cosmic time, the SKA will trace the cosmic web in 3 dimensions, revealing how vast flows of gas feed galaxies and fill voids. It could directly detect the primordial ripples from inflation, probe the nature of dark energy, and even listen for the faint, structured signals of intelligence, providing a permanent, sensitive ear for the next wow signal. Together, these telescopes form a complete sensory suite for the cosmos. Rubin watches everything that moves. Webb and Roman stare into the deepest past with crystal clarity. The SKA listens to the hidden skeleton of gas that holds it all together. Their data will not just provide answers, it will generate new, sharper questions. For every mystery we solve, like the Pioneer anomaly, these instruments will likely uncover 10 more that are even stranger, pushing our understanding to a breaking point we cannot yet foresee. The true promise of this new golden age is not just solutions, but better, deeper, and more profound mysteries. This journey through 25 cosmic glitches reveals a universe far stranger than we ever imagined. From the silent, geometric storm at Saturn's pole to the ghostly pull of the Great Attractor, from a single, unexplained 72-second radio shout to the colossal emptiness of the Boots void, we have charted a cosmos that consistently refuses to follow its own rulebook. These are not errors in our data or simple gaps in knowledge. They are profound contradictions, places where reality itself seems to be whispering a secret we have not yet learned to hear. Each anomaly, whether it involves a missing element from the Big Bang or a galaxy made almost entirely of shadow, is a direct challenge to our current understanding. They prove that our maps of the universe, for all their sophistication, are still rough sketches with entire continents of mystery waiting to be discovered. This is the true engine of science. It is not the satisfaction of a solved equation, but the thrilling disquiet of a persistent, nagging question that refuses to be ignored. These 25 puzzles are not signs that science is failing. They are proof that it is working perfectly. They are the unanswered calls that push us to build bigger telescopes, to run more complex simulations, to dare to imagine possibilities beyond our current physics. They remind us that curiosity is not a phase of childhood, but the permanent state of a species destined to look up and wonder. So the next time you find yourself under a clear night sky, remember this. You are not just looking at points of light. You are gazing at a frontier, a living puzzle of unimaginable scale. Every star, every faint smudge of a distant galaxy is part of a story still being written, with chapters full of mystery waiting for their solutions. Which of these cosmic anomalies baffles you the most? Let us know in the comments below. And if you want to keep exploring the universe's greatest secrets with us, be sure to subscribe. The cosmos has only begun to share its strangest tales.